Tonight, I want to talk about communications in Chapter 16, and I actually starting a little early tonight. Can't believe it. But usually I'm a little bit behind, but hopefully tonight we can get through this. This chapter is a pretty involved chapter, but it is not a chapter that I pretend to know a lot about. I do know some, but I'm not good at it. So don't look at me as an expert in this chapter at all. I've fallen on my sword more than once in this area, and there's nothing really that I can say about it other than beware, okay? So this chapter has two basic parts. One is called networks, and one is called protocols. And we try to cover both of these subjects in this chapter, although they're two different subjects. One is having to do with basically hooking things together and making them talk when you don't need to write a specific communication package that communicates between the two. The other one has the idea that there is no set communications package or program, and you have to write one. So there's two different animals. This is hooking together things that all you got to do is do the configuring, and this one is where you got to write a program and make it work. This is the much harder part than this, although some of this has been simplified over the course of time. But basically, this is something that you can fall into a trap and work a long time to get to work. Why is this a hard chapter? Why is this a hard subject? Because you can't see it. You can see something about it, but you can't really see these bits and bytes flowing down a network cable. It just is impossible. And one of the things that I did when I was my last hurrah at Owens Corning Fiberglass was I built a system that basically was a nightmare of cables, RS-232 cables, and I was basically well, one of the reasons I was never hired back was because they said that it was too hard to troubleshoot, and I believe them. It was very hard to troubleshoot. Okay, so can I have everybody's attention? This is my attempt to try to go through this stuff, although I'm not an expert at it. I'll be blunt. This is not my area. And I'll say this, I've said it before, and I'll say it. If you're interested in becoming a networks expert in a factory environment, the best course you can take is a CSET 2200 course, which is a course on local area networks, and the professor there is very, very good. If you have the free courses that you can take, it would be a wise investment to take that one, because CSET 2200 does set you up so that you can wire a network locally. So CSET 2200 would be your recommendation, okay? So that gets you started. And then basically in this environment, we are pretty much settled on Ethernet with TCP/IP. And that's pretty much the standard that we are using. The last 20 years, the last 25 years, this has been the standard. And before that, there were a lot of other attempts to do a lot of other things, but basically, Ethernet with TCP/IP has become the standard for communications between different devices on the factory floor. Computers to PLCs, PLCs to PLCs, PLCs to drives, to motor drives, that type of thing. It has all come down to Ethernet. Now, prior to Ethernet, there was this thing called DeviceNet, and it was a subset of CAN bus. CAN bus is a protocol, or it's a four-wire wired system, 2 wires of power, 2 wires of communication, of bit communication. in automobiles, and this was invented by Bosch. And this was a communications package that was invented. This was invented so that you could automate the this was invented so that you could do away with wiring harnesses in automobiles. DeviceNet was a subset of CAN bus, and it was used to basically automate networks in factories. It's a 4-wire system, and you could use a screwdriver to land the wires. It was a easy to set up network. It's a little bit easier than Ethernet to set up. You could use a screwdriver, but it's gone away for the most part. Now, if you're interested in DeviceNet, I did keep a few of the screens from the DeviceNet protocol package called Device Networks, RS Networks, and I kept a few of the screens from it so you could review it, but it's old and I do not need to go back and review it for the most part. But everything was set up as a local network with I/O and all that sort of thing, and you could communicate with DeviceNet. That's not the way that any of the networks that we have with Ethernet are set up, but that was how DeviceNet was set up. So I've kept the screens, but I'm not worried about keeping anything about it now. Okay, so we move on. Now we come down to what is accepted in the factory today. So you have these basically 3 pictures. You have the Ethernet IP, which is Allen Bradley, Rockwell. Then you have Profinet, which is the Siemens and basically Siemens and basically they're the ones who are the backbone of this one. This is the European standard. This is the American standard, and then everything else. And there's a few others, but not much. Okay. ABB is also part of Profinet. Now, which of these is an open protocol and which one is a closed protocol? You'll be surprised. This is a closed protocol. This is an open protocol. So you do not have to have any special chips in order to provide this protocol, but you do with the Ethernet IP. And this is a review of the various protocol packages that are out there. Profinet, DeviceNet, and Ethernet IP. And then this is Foundation Field Bus, Modbus, and Modbus TCP, and EtherCAT. These are some of the bigger ones. There's also HART, H-A-R-T. And when you move from the slower to the faster, this is what you move from in Profinet, or the Siemens protocol. Here you would have the speed, and it moves faster, and this would be a cable, and this would be an Ethernet cable. This would be a twisted pair cable. All right, so now we get down into the actual communications and the layers and all that kind of stuff, and I'm not going to go through that with you because I'm not going to hold you accountable for any of this stuff, except for down here. Okay, now in Ethernet, there is a problem. The problem is one of speed and what happens if you add devices. Basically, you have to have a layer, you have to build up protocol, or not protocols, but you have to build up sophistication levels, even in Ethernet, in order to guarantee that things happen in an orderly way. So here is the lowest level of TCP/IP. This is a configuration level. If I'm typing away and communicating with the PLC, this is the level that I communicate at. If I'm communicating between PLCs, this is the layer I'm talking about. If I want high-speed I/O, this is the level I'm talking about. And if I want drive communication, this is the layer I'm talking about. And this is from it happens when it happens to this is about every 10 to 20 milliseconds. This is to about every 5 milliseconds. This is to sub 1 millisecond. So you're guaranteeing here within a millisecond that you're getting data from point A to point B. Very fast, guaranteed. So you have to specify the level that you want. You do not just automatically get these levels. You have to specify these levels. This is something that I've personally not done, but I'm guaranteeing you, yes, sir. This is not all of them. This is just the Profinet, okay? But this has to be across the board for any of the networks. You have to be able to guarantee high-speed transmission. You have to be able to guarantee high-speed communication at the sub 1 millisecond level, and all of them have to do that. You have to be able to guarantee this, you have to be able to guarantee this, you have to be able to guarantee this. So you have to go to sophistication levels, and that means higher level of cards, higher level of everything in order to do this. And this, they can all go on the same wire, but this one has to have priority. This one has to have some priority, this one has to have less priority, and this one has no priority. So the priority level of the communication has to be highest of this one. But they can all exist on the same wire. Okay, now what are we really talking about? We're talking about communicating between devices, and we've not talked about that before, but you have, in the old days, you would have one big PLC, but today you have to be able to do this, and you have to be able to do it guaranteed all the way along. And if you want to have a system put together today, you have to do this. It works best if you size these according to the process that you want to encompass. So each of the computers that you put in, each of the PLCs that you put in, has to be sized for its specific function, but they can communicate with other devices up and down the line so that they can be basically allow the control to occur and flow between devices. Now, this is some of the I/O communication that you can get into. And this is called I/O link. And down here is one called ASI, ASI. It's a high speed. You can take it and pass it around again. Pass it to that side. Okay, thank you. All right. Now, some of this stuff is covered under the real PARs, and I've covered some of it with the real PARs. I'm not going to try to duplicate what they've done, and here's some of their stuff. There's a lot of stuff from real PARs on this. Okay, enough. So, how do you do this? Well, each of them have multiple ways of communicating from point A to point B. Allen Bradley has a message command, and also Siemens has a get and a put, but they also have other ways that are more sophisticated. This is the old RS Logic 500 way. Now, one of the things you can do under the communications is, I think it's an 8-point lab to be able to communicate between two PLCs. It's an easy lab to get running, and it doesn't take you a long time. But this is how it's done in Allen Bradley with a message command. And it only exists in the one that is doing the head. The message block only exists in the one. It does not exist in both. Okay? If you're sending or receiving, but you're the one who's doing you're the boss, that's where the message command exists. Okay, now with Siemens, there are three different approaches to being able to communicate between PLC to PLC. One is the get put. One is, there's another one, and then there's the RIO. The iDevice method is the preferred method, and this is the one that I would recommend if you're going to put the Siemens two processors together and have them talk. Use the iDevice method, and it's featured right there. And Michael Smith wrote a PLC communications, and there is his lab report right there. It's how it's done. So you can copy this if you want to. Cheers to copy. It works. So if you want to get a entry into this book, do something new, novel like that, and I'll put it in if you want me to. But this one works. This is right, here's the logic and here's the lab, and it's how it's done. So it's just plopped right in. Here's the other way, the T-send. No, this is the T-send. This is how it's done. Communications PLC to PLC. Okay, now I come to this kind of a transitional area where I have things that are dissimilar that need to be included together. Why would we ever have that? Well, because, I was going to say Modicon, because Siemens and Allen Bradley don't make every device under the sun. They make some devices, but they don't make them all. And you wouldn't want them to. You would not want Allen Bradley or Siemens to make every device in the world. You would say that'd be kind of bad. So basically, you have dissimilar devices, and sometimes you have to connect them. So how do you do that? ChatGPT, right? Well, AnyBus is one of the device platforms that allows you to do that. Okay, AnyBus. Believe it or not, it's called AnyBus. Okay? AnyBus works, as does others. This is another one. Red Lion has a series of devices that can communicate the similar devices. Hilscher is the one that we have in the lab. It's a German company. But if you want to communicate dissimilar devices, like an Allen Bradley to a Siemens, okay? Now, you can put the Ethernet IP protocol right into the Siemens PLC. So here's a Siemens PLC, okay? What it talks out of its port is Profibus, naturally, okay? But there is a add-on instruction or a special instruction that turns it into a Ethernet IP port. Yes, you can. It will, this software add-on will make this port an Ethernet IP port. It costs you with memory and time inside the device, but you can do that. I do not know if Allen Bradley does the same thing. I do not know. But I do know that you can do this. You can take this port and make it an Ethernet IP port. Why would that be important? All right, I've got a FANUC robot. What does it normally come with? Native Ethernet IP. Now you can order a Profibus or Profinet add-on card, but if you didn't do that and you wanted to just use this, how would you communicate with a Siemens program controller? You could communicate with an AnyBus card or a Hilscher card or a Red Lion card, or you could do this internal inside the PLC. It's your choice. Now, what are the things that you have to watch out for? There is a delay inherent in any of these devices. You have to be careful that that delay does not cause problems with your process. It could be 2/10 of a second. It could be, I don't know if it's any longer than that, but you can have delays in these. It's kind of like I take something in and I burp something out, okay? I listen in Spanish and I talk in French, okay? So I can do that. I can do that all day, right? I can't do that, but you know what I'm saying. But it takes time to process that. And by the time it takes to process that, you might have lost the time that you need in order to make your process run effectively. You say, how many processes are there like that? I don't know. You got to be careful. So this is an area of concern. Always ask the question, how long does it take to do this conversion process? How long? And it takes time. Every one of these is not cheap, either money-wise or time-wise. You have to ask that question. Okay, so have I ever done this? This is the Hilscher card. Have I ever had to do this? Yes, I've had to do this. And I'm not saying that I've been a victor every time. I have most of the time, but I've not done it all the time. Okay. So also we have on the Siemens, not on the Allen Bradley, but on the Siemens, we have an ASCII interface card that allows you to, on the front end of the PLC, here's your PLC, right? Here's your CPU card. Here you can have add-on cards over here. Here's my CPU. On the left, I can add a serial communications card. I can add an ASCII read-write card. Little 9-pin D shell connection down at the bottom of it. Okay? Now, with that, I can talk serial input and output. Now, is that a very effective way of communicating? The answer is no. It's slow, but it works. And sometimes that's the only way you've got of communicating with various things. Okay? Again, you can't see it. It just goes. You can, but it's hard. You can have a breakout box. You can put an oscilloscope on it, but it's hard to see. But you can talk out of one point to another. Now this is what it looks like when you're talking serially. By the way, which is faster, to be able to talk serially or parallel? Most people would say parallel, but serial is by far the fastest communication that you can get out of any device. Serial communication. All right? So this is what the bits look like, okay? A 1 is a high, a 0 is a low. So this would be a 1, a 0, 0, 1, 1, 1, 0, 1, 0, 1, blah, 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 okay? Now, if you don't think that that's important, that is a timed interval, that is exactly what that is. It's timed at a certain rate. So we talk about various transmission protocols and modes, and we talk about them in terms of either generic or by name, whose they are. And Modbus was one of the first ones. Modbus protocol was one of the first. Not one of the best, but it was one of the first. So as a result, it gets some mileage, okay? What happened was, a lot of things happened, but one of them was that Modicon came out first, then they got bought out by Gould, and they never got a chance to come back and do anything else. But they had a protocol called Modbus. It was a master-slave. Slave 1, slave 2, slave 3, etc., etc., etc. Now, what is good about this? You can set up a computer to do this. What's bad about this? You can set up a computer to do this, because basically you have to have a specialty device in order to get this to work. This almost has to be a computer, not a PLC. It's possible to do it as a PLC, but it's highly unlikely. Okay? So you have to have a computer. Then if this guy goes down, everything is messed up. Now, after they came out with this protocol, this is called a master-slave. Alan Bradley came out with what they call a peer-to-peer. This guy could talk to this guy, this guy could talk to this guy, this guy could talk to this guy. It was slower and all get out. You could see the bits going up and down the thing. But because there was no master, and a PLC could initiate a communication to another PLC, they trusted it. People trusted it. And this won over Modicon. This is how Modicon lost its shirt, even though they had this protocol. So basically, this was called a peer-to-peer. This was commonly referred to as the blue hose. A little history for you. When people talk about the blue hose, they're dating themselves because it was called blue hose back in 1985. 1982, 1985, this came out 40 years ago. But it won Alan Bradley over Modicon, and it basically put the final nail in Modicon's casket, or whatever you want to call it. So that's what did it, right there. Now, was this very good or was it very bad? It didn't matter. It was good enough. People accepted it. Now, also, we were communicating with all kinds of other devices, and we had these bits and bytes going up and down these wires. And basically, a protocol is a definition of what's going up and down those wires. Okay. This is kind of talking about the bits and the bytes going up and down the wire, what that means. And this is an example of a very simple protocol. It's a hi, how are you protocol. And this is sending a letter, and then a head number, a number, and then a checksum, and then an end of text. And then the response, and then you see if you can read it or not, and then a command. Okay, this was a one from a company called Pepperell and Fuchs. I was very closely worked on this process. What this was a very early version of RFID, okay? Which basically stands for radio frequency identification. So basically you had a disk that you could read or write to, and it would have memory on it, and you could read to it and you could write to it or you could read from it. And this was the protocol for that. Now, it happened that in the process of doing this, that I wrote this, I made a mistake, and I'll tell you about it in a minute. I'll tell you what I did. Here is the Modbus protocol. Now, the Modbus protocol is based on the Modbus addressing system, and if you notice that the addresses all start with the number 1. So discrete outputs, in other words, zeros and ones, outputs, start with 0, 0, 0, 0, 1. Discrete inputs, that's ons and offs, discrete bits, start with 1, 0, 0, 0, 1. So the first one is 1, not 0. Maybe nobody here will ever have to do this, but you will thank me mightily for identifying the fact that the first address is 1, not 0. Because if you assume, like most people, that the first address in any file starts with the address 0, you will always be off by 1. And it's very unforgiving. And you will fight this until somebody tells you, some old person like me, that the addressing starts with Modicon at 1, not 0. Any questions about that? This is the kind of thing that it's buried in the literature, but it's real, and it will bite you if you don't do it, if you don't know that. So here's the code for the query. If you send it an 01, you're going to be reading coil status. If you send it an O2, you're going to be reading input status. If you're sending it an O3, you're going to be reading holding registers. If you're sending an O4, you're going to be reading input registers. If you're sending an O5, you're going to force a single coil, et cetera, et cetera, et cetera. Now, I've shown with that some actual transmissions, okay? I hate to say this, but I may resort to giving you a problem like this on the test, okay? I don't know. Don't be afraid right now, because we're going to have a review, and I'll talk about this again in that review if I'm going to ask you this question. I've fought this, because this is one of the questions that is a numeric question with a right and a wrong answer. And if you don't know what you're doing, you'll spin your wheels until whatever. But I do want you to all know extremely thoroughly that addresses start offset from 1. From 1, not 0, from 1. So the first address in this starting this thing is from address 1. So here I'm saying C4, which is a hex number, which is 196 from address 10001. So my starting number is what? Where am I looking? I'm looking at starting at 10197. So if I wanted to make something hard, you can't make it any harder than this. 10197, and say how many do I want to see? There's 4, there's 8, there's 12, there's 16, 20, 22. So I say I want to see 22 bits starting at address C4. And how's this a 22? How is 16 a 22? What is this number right here? It's a hex. This is 16 plus 6 is 22. It's not easy. This is a hex number, this is a hex number, and this is an offset from 1. If you get those two things, you're in. So what's my response? Byte by byte. AC. What is this? 1010. That's an A. What is this? 1100. That's a C. So here's my AC. AC. What's next? 1101. D is in David. 1011. B is in boy. So here's my next one. DB. And here's my next one. I don't care what these two bits are because I didn't ask for them. They could be ones and all. I don't really care. All I have to do is say they don't matter. They're zeros, and this is a 1 and a 1. Now you say, when were they a 1 and a 1? At the instant that I sent the transmission. So this is a 1. This is like taking a little picture of that memory at that instant in time. Do they stay the same? No, they can be moving. They can be. All of these bits can be changing, and they can all be different in a second later. But at that instant in time, I ask for, what are they? And it dumps it out. It dumps out and tells me what they are. So this is a shot and a response. If I wanted to get it again, I have to do another shot. Ask it again, and then it gives me another response. Everybody follow that? That's all this is. This is very crude. So you're taking pictures of the memory at certain points. And every time you take a picture, you have to send a query, and then you get a response back. That's all this is. Any questions? Any comments? How dumb can it be, right? Now, you might ask, is this still in use today? The answer most definitely is yes. This kind of protocol, and this one especially, is still in use today. You'll still run into it. I ran into it. Well, this is kind of dating me, but the last project that I did was for a steel plant. It was not it was a privately owned company in 2009. 2009 in LaPorte, Indiana. And in it, they had 3 Merrick Lawson weight feeders. And the Merrick Lawson weight feeders communicated to the Allen Bradley through Modbus protocol. And you can say, but they're Allen Bradley, they're not Modicon. Yes, they are. But in order to communicate to these Merrick feeders, you had to go through Modbus protocol. So what they did was, this is really strange, they went out from the PLC, what they call it a high-speed data highway plus, not even Ethernet IP, but it was a data highway plus. They went to an Anybus port, and out of it there were 3 cables that were going to the 3 Merrick Lawson weight feeders. And this was Modbus plus. This was, Modbus. And this was Data Highway Plus. So inside of here, inside of this guy, I was saying how much to feed these Merrick feeders, how much of this was going to be dropping onto the belt. I communicated how much they were per unit of time. In other words, so many pounds per minute or whatever the delivery rate was, I basically did. Piece of cake. I had it up and running in about 30 minutes. And somebody looked at me and said, how do you know that? How do you do that? Because I've written this stupid protocol before and I've worked with it before. But the key to the whole thing is you start from offset of 1. Everything else flows. But that's not in the literature. They don't tell you that. They just assume you know it, and it'll get you, because most people assume the offset is from 0. And it's not in that case. I have no idea whether I'll ask you a question like that or not, but I gotta be honest with you. If I don't ask you a question like that, I need to tell you one way or the other. You need to review these questions and then be willing to do one. I'd love to just ask you, do you all promise to remember that the offset from Modicon or Modbus is 1? And if that's the case, then we can forget about this and go on, because everything else about it is pretty straightforward and easy. But if you don't remember that, can you understand? You'll always be off by 1 if you don't do that, if you don't remember that. And I'm telling you, it could be days. You could be working on this for days or weeks until you get it to work. Because why is this working? Why is this working? You'll assume everything else under the sun, and then you finally, somebody old like me will say the offset is from 1, not from 0. Okay, enough on that. Now this is the RFID project that I did that flopped. Okay, and I'll tell you why it flopped, and I'll tell you exactly why it flopped. Okay, now I got it eventually to work, but it happened in such a way that I never got to see the final version of it. But I had it. It was working 95% of the way, and then I got. By the way, if you are a consultant and you get laid off, is that bad? No. As long as you get paid, you're okay. And I was 95% of the way through it, and I had gotten this problem pretty well solved, but they laid me off, and they said, today's your last day, Ted. And I said, I'm that far from being finished. Today's your last day. I packed up my stuff and left. Consultants are like that. You have to be able to have a thick skin and go on. But I got paid. So again, if you get paid, it's okay. Just accept it and you go on. Consultants, it's a different world. Consultants, sometimes they want you, sometimes they don't want you, and they get you started and then they back out or whatever. The one where I told you about the thing I solved in a day, I should have asked them, I'm not a good marketer, and I should have said, I'll solve this problem for you for $20,000, and they would have paid me. They would have been so happy to have paid me, $20,000 to have solved that problem for them. I walked out of there in a day with it solved, and I got $35 an hour, which is not that much money. But on the other hand, I had the satisfaction that I got it working, and that's something that none of them could do. So I had that satisfaction. But that's about it. This is one where again, what happens when a proc switch turns on? If a proc switch sees something, what's it going to tell the PLC? It does this. Not guaranteed, but that's typically what it does. Okay? That's called a noisy front end. If you can't figure that out, it goes blip, 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 on whatever. Now, this program was tripped by this proc switch. So this program, this guy turned to this guy, who went to this guy, who went to this guy, who went out here to read. Then it came back to this, to this, to this, to this. And these were all slow. This took about 5 seconds to do this complete thing. What did I just tell you here? How much time is in between these? About 1/10 of a second. So what actually happened? I started one, and it got to here, and it got to here, and then I started another one. It never came back to here, okay? Right? Now, what happened when that blessed event happened? This one went bonkers. If it saw another communications from the front end before it got the receipt from the back end, what do you think happened to it? Any ideas? It locked up. The only way to restart it was to power down and power back up. Okay? Now, I had this working on the bench in my office. I pushed a button, saw it work, down and back, beautiful. Walked out on the factory floor, and it hung up again and again and again. So what's the message there? Don't always trust yourself with what? Something working on a bench. It can work in the real world, or it can burp. And this is one of the times when it burped. So it took me a while to get this fixed. I finally got it fixed. Anyway, any questions about that? What's the message here really? Keep the lines of communication simple. This was not simple. I didn't buy this. This was something that was bought for me. I just had to program it. But keep the lines of communication simple and keep the number of computers. Each one of these has a CPU in them. Okay? These don't, but these do. This one had a CPU, this one had a CPU, this had a CPU, and this had a CPU. Every one of them did. And it was not Ethernet speed. This was fairly slow, fairly slow, fairly slow, blah, 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 blah. End of story. So anyway, I'm telling you that to help. You'll make your own mistakes. You'll probably make the same ones that I made, but this was a huge one. But anyway, I got it to work finally. So what do you have to do when this happens? Seal this on until you get a response back or until you have a 5 or 10 second timeout. That's what you got to do. So seal this on for at least 10 seconds. That was my fix, and it worked. What's this? Well, this is Struthers Martin. Who's this? Paul Newman. What is this? What is this about? Academy Award winning picture show of 1969, Cool Hand Luke. Okay? I was in college when this thing came out. And I think I watched it about 3 times. I went to the show about 3 times and watched it. It was about a renegade, a rebel, that type of thing. This guy was a rebel, and they finally shot him and killed him. But in the meantime, he didn't let them tell him what to do, okay? This guy is Struthers Martin, and what did he say that has anything to do with this course and this chapter? What we have here is a failure to communicate. Famous line. Famous line. So if you never watched that show, that's okay. But now you know the famous line from Cool Hand Luke. What we have here is a failure, and he said it with Southern drawl. What we have here is failure to communicate. I can't mimic him very well, but that's what he said. Anyway, and they eventually shot him. I don't want to spoil the show for you, but it's not a pretty ending for this guy. Okay, now, of all the things that you've gotten into so far, I want you to start looking at this. Because why? This is some of the choices that you have under version 16 of the processor for the communications protocols. Now, this is not playing games with you. This is saying some of the remote communications that you probably never punched into on the Siemens processor, and I'm sure Ellen Bradley's got some of the same stuff, but look at all the stuff you can do. And it goes on. And it goes on. And it goes on. And this is the standard stuff. This is not the specialty stuff you can download from off the internet and get. And it goes on. You can even turn one of these into a web server, supposedly. I've never tried any of that stuff, but again, you can try it if you want to. So what am I telling you? You'll never stay up with it. You'll never understand all this stuff. You'll never get it. You just have to use the things that you can use and learn them as best you can and do the best you can. Here's the Modbus thing with the Anybus. You'll never get it all. You'll never get it all. Here's a web server for easy internet connect. So you want to get your PLC on the internet? Right, here it is. Because you got to do it. Okay, so now we get into some things that can matter. What is IEC 62443 from my buddies at ChatGPT? International Standard Series for Industrial Cybersecurity, specifically designed to protect industrial automation and control systems, such as PLCs, SCADA systems, DCS, and industrial networks. Published by the International Electrotechnical Communication, is widely regarded as the global database baseline standard for operational technology for cybersecurity. Okay? How's the best way to keep something safe from cybersecurity? Unplug it from the network. Okay? The best way. Just keep it isolated. But you can't always do that. If you can, that's my first suggestion, is unplug it and let it stand on its own. As far as you can tell, let it stand on its own. But these are some of the things about it. Is this important? Yes, it is. Okay, so there is a standard. So as you're writing your specifications for their various pieces of equipment, what would you say? Must be compliant with IEC 62443 standards for what? Network security. In other words, don't put something in my factory that isn't secure to the best of your ability. And here are the problems with Modbus. And I have not made up my mind whether I want to ask you a question about this or not. I tend to not, but on the other hand, Don't know. I got to work that out on my own and come up with an answer. I do not have a clue, really. We're not even close to the end of this chapter, by the way. There is so much in this chapter, it's unbelievable. This chapter is there's way too much in it, and yet, I feel helpless at times because there's way too much. When I showed you all that stuff from Siemens, that listing of instructions for various kinds of things, okay, and this is the PLC to PLC communications we saw earlier. And more, and more, and more, and more, and more. Here is connecting Cognex to Rockwell. And by the way, somebody asked me about how do you get Allen Bradley up and running? When you open an Allen Bradley program controller out of the box, it is dumb as a rock. It is not able to start up right away. You have to flash it, okay? And this is the program that you use. This is a separate entity. It's a Rockwell product, but you have to give it a version level. We are at 33 for our version of Allen Bradley. But you have to do this. You have to do a control flash. It'll do it. You cannot unplug it while it's doing it, but that's the process. So that sets it up, gives it a firmware version, and away you go. When I was working with the older processors, they had a little memory card. And as those processors got older, they got to about 8 or 9 years of age, they would lose their memory, they would lose their operating system. And I was getting so good at reflashing those that, and I finally said, the heck with it and threw them away. But for the longest time, 2 or 3 years, a couple years, I became very good at flashing the memories of those cards. If you get to the point where the program controller loses its memory, you should throw it away. It's not worth keeping. And I kept it because we couldn't afford anything else, but I did not like it. Okay, and that's about the end of this. 58 pages, but there's a lot there, and I don't want to scare you, but there's just a lot in that environment. What's hard about this? You can't see it. You cannot see it. Okay? Did the candy get all taken? The bag is empty, right? Wherever the bag is, it's empty, right? Or does anybody know? It's not back up here, so I'm going to assume it's empty. Good. Good deal. Anybody have any questions? We're done a little early today, but I started a little early, so I'm not really going to worry about it. We're done with no, we're not. We've got one more chapter, chapter 18, which will take all of about 20 minutes to talk through. But I'll, on Monday of next week, I'll give you a good idea as to what's going to be on the test. I'll have thought through it and given you some good hints as to what's going to be on the test, so that you don't have to study everything. You can't study everything. There's no way. But I'll have given you maybe a list of 15 or so questions that you can think about, and I'll have that as a base for the test. The test will then be, I think, on Monday night and finals week. I'll give you till Wednesday high noon to hand in all your projects. And dirty little secret, I'll go to Thursday morning at 8 o'clock in the morning. I say high noon on Wednesday so that everybody who is the procrastinator will say 5 o'clock. They're running in here with their last one, and they'll say, "Can I still do this?" Yes, you can. But by 8 o'clock Thursday morning, if it's not under my door or it's not handed to me by 8 o'clock in the morning, I can honestly say, you didn't hand it in by Wednesday noon, you didn't hand it in by Wednesday in the evening, you had all that time, sorry, it's too late. I do my grading, get my grades averaged up, done like that. Give everybody an A. Oh, I shouldn't say that. I don't, but I'm fair, and I think I do. I'm more than generous, so I think you can appreciate that, and hopefully we all have a fairly good experience out of this course. I don't want to sink anybody's boat. I don't want to scare anybody, but I think I've already done that. So I think I've done a pretty good job of scaring you, which isn't all bad. By the way, I was, and I'm not proud of this, but I was at a conference not about a year ago, right about now, at a conference, and they were talking about equity, and I'm not against equity in some cases, but I asked the person who was giving the speech, I said, you've got to graduate folk, and then they go out in the real world. And I said, what do you tell a person when they are standing in front of a machine that they've got a program to run on a certain day to make a product? And how do you justify, how do you transpose from, everybody gets the same, everybody's traded the same, blah, 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 and everybody gets the same to that? And I said, how do you do that? No answer. You will be held accountable. It will be one of these days, if you work in industry, where you will have to start something up, something you've designed, something you put together, and by a certain day, at a certain time, it will have to start up. Now, there's three parts to that. What? It has to work. It has to be on time, and it has to be under budget. Which of those three can slide? You can delay it, and you can cost more money, but it has to what? It has to work. Okay? There's no compromise in that arena. It has to work. I've seen projects slide in time. I've seen projects slide in money. But at the end of the day, they either work or they don't. And I'm looking at the people who are going to make it happen or not happen. So you have to accept that there is some point in time when you're going to have to stand there and make something work. So hopefully this prepares you a little bit for that. That's the goal. That's